So today we are going to go through Unit 9.1 States of Matter. In this period, we will learn about states, solid, liquid, and gas. First, state. State is the one of the distinct forms in which matter can exist. That means state can have melting and boiling points. State is divided by 4 parts: is solid, liquid, gas, and plasma. But today we are just going to go through solid, liquid, and gas. First, solid. Solid has a lattice shape, which means that a lot of molecule is combined together. It has fixed volume and fixed shape. That's why you can hold it. Liquid. Liquid has a fixed volume and takes shape of the container. Liquid cannot compress like gas. Gas had no fixed volume and takes shape of the container. Gas can be compressed because between the gas particle is a lot of space. This is the state conversion. From solid to liquid, we call that is a melting conversion. And the evaporation happens when liquid is converted into gas, and condensation is which gas is converted into liquid, and freezing is which liquid is solid. There is a special way to convert solid to gas, which is called sublimation. And some of the scientists say that gas can be converted to solid by the desublimation. We will learn about this in the next period, and you will have a lot more knowledge. Thanks.
We'll be representing 9.2, the kinetic model of matter. So first off, we'll be explaining the Brownian motion, or also the evidence for the kinetic model of matter. So in here we have a box. So the moving particles are constantly baffled by the fast moving particles of the air. So the air particles are the pink ones. So this is the evidence for the kinetic model of matter. So first off will be solid. So here's a picture of the solid particles. Its movement is tightly packed, so it does not move around much, and it vibrates in a fixed position. The hotter object, the more it vibrates. Its arrangement is packed closely together. It has close contact with its neighbors, and except it's liquid. This is the picture. And its movement is less tightly packed, so it moves around within the bulk of a liquid, and it both vibrates and moves around. Its arrangement is packed less closely together, so it is in contact with most of the neighbors, and its orders are pretty much disordered and jumbled. And lastly, gas. Gas moves freely about and it collides with each other and the walls of the container. Its arrangement is widely spread, and it is no longer in contact, and it only collides. Well, we explain evaporation. So, water evaporates into water vapor before it reaches 100 degrees Celsius, or the boiling point. So why is this? So, particles of water is moving around, and some are moving faster than others, and these may move fast enough to escape the water surface.
Chapter 9.3, Forces in the Kinetic Theory. So far, we have seen how the kinetic theory of matter can successfully explain some observations of the ways in which solids, liquids, and gases differ. We can explain some other observations if we add another scientific idea to the kinetic theory. We need to consider the forces between the particles that make up matter. So why do the particles that make up solid or liquid stick together? There must be attractive forces between them. Without attractive forces to hold together the particles that make up matter, we would live in a very dull world. There would be no solids or liquids, only gases. No matter how much we cool matter down, it would remain as a gas. Another way to refer to these forces is to say that there are bonds between particles. Each particle of a solid is strongly bonded to its neighbors. This is because the forces between particles are strongest when the particles are close together. In a liquid, the particles are slightly further apart, and so the forces between them are slightly weaker. In a gas, the particles are far apart so that the particles do not attract each other and can move freely around. What happens to these attractive forces as the solid is heated? The particles start to vibrate more and more strongly. Eventually, the particles vibrate sufficiently for some of the bonds to be broken, and a liquid is formed. Heat the material more, and eventually the particles have sufficient energy for all of the attractive forces between particles to be overcome. The material becomes a gas. And in a gas, the particles are so far apart and moving so fast that they do not stick together. If you cool down the gas, the particles move more slowly. As they collide with one another, there is more chance that they will stick together. Keep cooling the gas and eventually all the particles stick together to form a liquid. More about evaporation. Evaporation is different from boiling. A liquid boils at its boiling point. All of the liquid reaches this temperature and it gradually turns into gas. But evaporation happens at a lower temperature, below the boiling point. We have seen at the end of section 9.2 that the kinetic model can explain why a liquid cools as it evaporates, because it is the most energetic particles that are leaving its surface. Now the particles of the liquid have less energy, and so the temperature of the liquid decreases. If the liquid is in contact with another object, energy will transfer from the object into the liquid. And this is why you feel cold when water evaporates on your skin. The water gets colder as it evaporates and energy leaves your body, transferring into the remaining water. We can use the kinetic model to explain some more observations concerning evaporation. If a liquid evaporates more rapidly when it is hotter, that is because at a higher temperature, more of the particles of the liquid are moving fast enough to escape from the surface. A liquid evaporates more quickly when it is spread out, so that it has a greater surface. Because with a greater surface area, more of the particles are close to the surface, so they can escape more easily. And when you see that a liquid evaporates more quickly when a drop flows across the surface, that is because a drop is moving air. When particles escape from water, they are blown away so that they cannot fall back into water. Moving on to chapter 9.4, gases and the kinetic theory. We can understand more about gases if we think about the particles of which they are made. We could consider the following questions. For example, why does a gas exert pressure? What happens to a gas when it is heated? Or what happens when a gas is compressed? If you blow up a balloon, your lungs provide the pressure to push the air into it. Tie up the balloon and the air is trapped. The pressure of the air inside pushes outwards against the rubber, keeping it inflated. The more air you blow into the balloon, the greater its pressure is. This picture shows the particles that make up a gas. The gas is contained in a square box. The volume of the box is the volume of the gas. The gas has mass because each of its particles has mass. If we weigh all the particles individually and add up their masses, we would find the mass of the gas. So why does a gas exert pressure? Because its particles are constantly colliding with the walls. They bounce off the walls, exerting a force as they do so. What happens to the gas when it is heated? When it is heated, it is given more energy, and the particles are moving faster. So the higher the temperature of a gas, the faster its particles are moving. What happens when a gas is compressed? With the same number of particles in half the volume, there are twice as many collisions per second with the walls. The result is twice the pressure. Observing Brownian motion of smoke particles in air allows us to deduce something important about the motion of air molecules. The air molecules are much smaller than the smoke grains. In other words, they are very light compared to smoke grains, and yet they can cause the smoke grains to move around. The air molecules can only do this if they are moving around very fast. In fact, the molecules of the air around us move at the speed of the order of 500 meters per second. That is a little faster than the speed of sound in air. Now imagine these high-speed molecules rushing around in a room. They collide with the walls, the ceiling, the floor, the furniture, everything. They bounce off every surface, and in doing so, they change direction. Each collision thus results in a change of momentum of the air molecules. Each molecule that collides with the surface exerts a tiny force. Because there are so many fast-moving particles, and because they collide so frequently with all the surfaces in the room, they exert a large force. This is why a gas like air exerts pressure. Moving on to Boyle's law. This is a picture of an apparatus used in the investigation of Robert Boyle. In this apparatus, some air is trapped inside the vertical gas tube. The oil in the bottom of the apparatus can be compressed with a pump so that it pushes up inside the tube, compressing the air. The volume of the air can be read from the scale. The pressure exerted on it by the oil can be read from the dial gauge. By increasing the pressure on the gas, its volume decreases. This table shows some typical results. But can we find a mathematical relationship between the pressure P and the volume V of the gas? The relationship between P and V was investigated by Robert Boyle, an English physicist and chemist. He published his results in 1662. The relationship that Boyle found can be stated in a number of different ways. Number one, doubling the pressure has the effect of halving the volume, and 3 times the pressure gives 1/3 of the volume, and so on. Number two, this graph shows that increasing pressure leads to decreasing volume. Number three, again, this table also shows that relationship. From the last column in the table, we can see that the quantity pressure times the volume is constant. So we can write P times V is equal to constant. Number four, initial pressure times initial volume is equal to final pressure and final volume. Where P1 and V1 are one pair of release of pressure and volume, and P2 and V2 are another pair. Number 5. If one quantity decreases like this as another increase, we can say that one is inversely proportional to the other. Using this symbol, which means is proportional to, we can write P is proportional to 1 over V, or V is proportional to 1 over P. Number 6. This graph shows that plotting P against 1 over V gives a straight line graph passing through the origin. Finally, we can write the relationship in words. The volume of a fixed mass of a gas is inversely proportional to its pressure, provided its temperature remains constant. This last statement is known as the Boyle's law. It is important to understand why Boyle's law includes the phrase provided its temperature remains constant. When a gas is compressed, its temperature rises because energy is being transferred to the gas, and this tends to make it expand. In the Boyle's law experiment, the trapped air soon loses energy to its surrounding and cools back down to room temperature. While it is hot, its volume is increased. Only when it cools down will we find that it obeys the relationship P times V is equal to constant. Thank you for watching.